Howdy, my name is Jian Tao. I'm a assistant professor from the College of Performance, Visualization and Fine Arts at Texas A&M University. I'm also a director for the Digital Twin Lab here at the Texas Institute of Data Science, Texas A&M Institute of Data Science. And today, we'll bring you the GPU programming introduction to CUDA short course through the supporting by the NSF grants, and also through the Accelerating Computing for Emerging Sciences program. This is part of the collaboration with the Texas Advanced Computing Center, High Performance Research Computing, and also University of Illinois Urbana-Champaign. There are essentially 4 parts for this short course. So we'll get started with the ACES for about half an hour. And then I'll talk about GPU as the accelerator for about half an hour as well. And then we'll get into the some hands-on part to get started with the CUDA execution on ACES. And finally, we'll get into the details about the CUDA programming. So first, let's get started with the ACES. So ACES is a computing system, and it's supported by National Science Foundation through the NSF Award 2112356. It's one of the 2 composable clusters that we are currently running at HPRC. ACES is one of them, which is a primary focus for today, and the FASTER is another one. Both are funded by National Science Foundation, and they have very similar structures, but different scales. So what is composable clusters? Composable clusters is different from traditional HPC systems, and given a hardware system, it's already fixed. If you have 1 GPU inlet, you have 1 GPU inlet, and when you allocate your resources, you only can allocate 1 GPU per node. But for composable architecture, through the liquid system, so we are able to allocate up to 16 GPUs per job. So your job can send a request through the Slurm job script and ask for more than 16, I think up to 16 GPUs per job. And of course, this could be a hybrid system. You can request, say, 5 FPGAs, 3 NVIDIA GPUs, and probably some more other hardware that are currently supported by Liquid. And that gives the user the ultimate freedom to pick the system that's needed for testing different acceleration scenarios. And also it's a wonderful testing platform for AI and machine learning applications. So more information about ACES system and this architecture, you can visit the ACES system link, which is provided in the slide. To get access to the ACES portal, ACES system, you can use the ACES portal, which is built on top of the open on-demand portal. And you will need your access ID to log in that. I'll show you I'll lead everyone through this quickly in a second, but let's go through this slides first. You all need to have your access CI token ready, and then access ID ready. And then if you have any trouble to get access to the system, feel free to reach out to us at HPRC, or you can reach out to Access supporting desk that can help you to get you started with the Access system. So for today's short course, we'll be primarily using the command line interface. So the Open On Demand has this web-based share access, which is very convenient for those who are new to the command line interface to get started quickly. For those who are already familiar with command line interface, this is just the same. It's just the only difference is that this is not like terminal-based. It's a web-based interface for you to log on to the system. And of course, you'll have some extra features through this Open On Demand portal, and you can copy down the files and modify, edit files directly through the portal interface. So I'll have some example about it. So before we jump into moving to the next slide, I'll show everyone how to use this portal and get everyone started first. To get there, I'll type hprc.tamu.edu. That's our HPRC official website. If you click a portal, move your cursor to portal menu, and you'll see some drop-down menu items, and move to ACES portal access. It will point you to the I'm sorry, it's already logged in here, so you won't be able to see the login interface from the ACES interface, but you need to type in your credentials and get yourself authorized to use the system. Okay. I'll give everyone probably a minute or two just to get everyone there. Okay, good. Dual authentication will be needed if you are already using that. Okay. To get access to the shell command line interface, you click clusters and click ACES shell access. You'll be pointed to this command line interface. If you are here, you're all set. I think that's all we want to get here. That's everyone should be able to log on the system and get to this front line interface, the command line interface. Yeah, feel free to let us know if you have any questions. The slides might be a little bit different just for us. We are updating this to meet the latest needs for the to match the environment we have and also the latest information that we have. But it's essentially the same as the one you can get the slides online. I'll also share the PPT files with you a bit later. It's a Python. I'm sorry, Google Slides. Okay. Okay, let's move to the NSF ACES system. So what is ACES? ACES is Accelerating Computing for Emerging Sciences. It's a project funded by National Science Foundation. HPRC is leading the effort. The majority of the funding is put into the hardware purchase with extra support from NSF to supporting the system as well. It's part of the NSF Advanced Computing System and Services, CI, which is a cyber infrastructure testbed. And it offers a combination of multiple different accelerating architectures for numerical simulations and AI, ML workload. We are also providing consulting, technical guidance, and training to researchers. And this short course is just one of the efforts that we are offering to the community. And we are also looking for collaborations on computational and data-enabled research. If you have any interesting project you want to run on the system, needs any help, and want to work on collaborative research proposals, feel free to reach out to HPRC. So the ACES system is physically located at the West Campus Data Center here at Texas A&M University. And the system has been there for more than 2 years, I believe, so far, and it's one of the main systems hosted by the data center, West Campus Data Center. The system is essentially connected with the InfiniBand network. As you can see at the top, we have multiple login nodes and different data transfer nodes. Those are providing the user interface for people to log in. Like the user interface we currently use is the Open On-Demand user interface. It's essentially part of this front end. And whenever you get your job ready, job script ready, you can do the job submission, and then the job will be sent to the backend, and then it will be executed in the computing nodes. We have some extra nodes like the NEC vector engine nodes. Those are not directly linked to the backend. Those are separate ways, but you can still have access to those graph core pods and NEC vector engine nodes separately. But at the backend for the liquid system, that is really composable. we have different configurations. We have four essential configurations with generation 4 PCIe composable capabilities. We have extra 4 with generation 5 PCIe composability supported by the hardware. So it's a different generations of hardware supported in our system. And depending on your application, depending on particular configuration you need for your final hardware requirements, you might be using different generations. So, the generation 4, generation 5, depending on which particular hardware system you are looking for your testing and the development work. So this shows a summary of the system that I just mentioned. It has, as I mentioned, has a lot of computing power. And for more information about the detail about this individual systems, you can watch the ACES tutorial videos as well as other online videos that HPRC have been offering. We had short courses about these systems a while back. There are multiple accelerators on ACES, as I mentioned as well, for different systems, different queues, different partition in your queuing system, job script. You may be able to specify different accelerators you want to use for your testing and for your development work. More information could be found at the ACES hardware link provided below. The system software stack is essentially the same as all the other HPC systems that you may have used before. Most of the HPRC systems are using almost the same software stack, and they are almost the same almost everywhere. When you're getting to big centers, you might be using Slurm for job script. You have Lustre for the storage system, etc. So it's pretty standard configuration for HPC systems. To submit your job, you need to tell the job script what particular partition you want to use, so that the job will route your job to a particular queue that with a specific kind of accelerator that you want to use. So this shows the node and the partitions. And for those who are not familiar with the Slurm and job submission, you probably want to refer to the previous YouTube videos that HPRC is offering. You can find those on our YouTube channel. This is a sample job script that on ACES. You can specify how many GPUs you want to use and how much memory you want to use and how long you want your job to be, etc. So again, this is a template for your real job script. You need to definitely modify that based on your needs. We'll have some example to get back to this a bit later. Okay, with all that said, that's the introduction for ACES. And now let's switch gear to talk about GPUs. So GPU has been used as accelerator ever since CUDA ever since NVIDIA started pushing out the general purpose GPU, which is able to do things beyond what GPU was originally designed for. And GPU was originally designed to do video processing, graphics, computing graphics. And CPU was supposed to be doing the general purpose task processing and task handling, data processing. So with the general purpose GPU, people start writing code to offload computing tasks from CPU to GPU. That's how we use a GPU as accelerators. For those of you who might be familiar with FPU, that's like many years ago, there was a CPU was not very good at floating point operations. So there have been efforts to develop so-called FPU, floating point processing unit, floating processing unit. Later on, FPU got integrated into CPU, and now the CPU actually can handle those floating point operations much better. But again, with more and more tasks that need to be processed, a lot of data to be processed, the GPU turns out to be very good and interesting architecture to utilize for accelerating and offloading certain tasks on CPUs. This shows the latest, this is a snapshot, a picture of the latest Tesla B200 GPU. It has 208 billion transistors. And it's launched recently, I think during the GTC 2025. Some of you might already attended the GTC conference or watched the video, watched the release of this fabulous B200 GPU. It has a tremendous amount of computing power, but without a software, it's just a piece of hardware, right? To really leverage the power of this monster is to use tools that we'll be learning today called CUDA. And CUDA can fully release the power of this kind of device. And just like many other programming languages designed for different tasks, CUDA was developed to fully leverage the GPU computing power. Of course, it's supposed to be was designed to be a generic programming framework, but it turns out it's a very, very highly optimized framework and programming libraries that NVIDIA has been leveraging to dominate the market in the machine learning, AI, supercomputing, HPC, etc. So it's one of the if you consider hardware is part of the story, and software is another important part, and actually helping and to contribute to the big boost of AI and machine learning in the last 10, 15 years. So this diagram shows an overview about the so-called accelerated or how to accelerate science application. To accelerate scientific application, you start with application which was supposed to be running on the traditional machine, assuming it's for example C or C++ code or Fortran code, which has already been optimized to work pretty well on the GPU. Now the thing is that for the application code, there are always part of code that could be parallelized, that part of code cannot. I mean, all the way go from 0% to 100%. That's always, you can do that. So there's a very famous law called Amdahl's law, which the Amdahl's law tells us that given the application, if you know the certain part of the code could be parallelized, the maximum performance or parallelization that you can achieve will be fully determined by those parts that cannot be parallelized. Well, I mean, you can say the same for the parallelized part, but again, the whole idea is that given a piece of application code that you are supposed to be working on and help to make it faster, there is some upper theoretical limit that you can, how fast you can turn this to, no matter what hardware you're using or what algorithm you're using. So always an upper limit. So Amdahl's law tells you the upper limit for this kind of so-called strong scaling applications, that when you want to keep the same problem size and try to parallelize it, and what's your maximum gain when you're trying to do this? A very simple thought experiment you can think about. Let's consider you have probably 10% of your code can be optimized, can be parallelized. Okay, only 10%. Okay, 90% of your code is serial code. You cannot parallelize. You probably need to deal with I/O, or probably you want to do some other operations that cannot be executed in parallel. Okay, so this is just some extreme case, but let's just consider we only have 10% that could be parallelized. Now, given this 10%, given this 10% of code that could be parallelized and giving you the best parallel computer and the best algorithm, assuming you can 100% parallelize this 10% of code. Okay. I'm sorry, just everyone can just follow me. It's kind of interesting thought experiment. Assuming someone give you some bigger machine with 1 billion cores, and you can run your job perfectly, ideally, on those 1 billion cores. So total time taken for you to run this 10% of your job could become 0 in the ideal case. But that's the extreme case. That's like an ideal case when you can fully parallelize your 10% of your code. Now, with the rest of 90% of code cannot be parallelized, the speed up you can get is what? So assuming previously you run your code, it will take you 10 seconds, for example. Now, after you get 10% of the code fully parallelized, that goes to zero because it's fully parallelized, right? It's with unlimited resources. You can run your code only to 9 seconds. Okay, with a lot of effort, with a lot of resources, your benefit, your speed up is what? Your speed up will be 9. You get extra speed up with extra, the total is 1/9 divided by 1/10 will be actually 10 divided by 9. You get 10 divided by 9 speed up. It's like a 10% speed up. That's your maximum performance you might gain with this. So that gets to one of my very first question, and actually comments, more like a comment. Before you start working on your application, try to port that into GPU and spend a lot of resources and time, it makes sense for you to sit down and analyze your code first to see if you really can get what you get. Because this application code is highly dependent on the application, of course. And you, as a domain expert, you know much better than anyone else about what your code is doing. For certain applications, the parts could be parallelized, actually could be easily estimated. If you can 99% could be parallelized, you can get 100 speed up. If only 10% could be parallelized, no matter how much resource you're using, how good you are, you get up to 10% speed up, and that's it. So that's Amdahl's law. Of course, there are different estimations, but this is just rough estimation about a theoretical peak performance you may get if you know or have a good idea about how much what's the percentage of code could be accelerated. That's getting exactly to my point. When we try to start application your code, you need to understand your application first before you start jumping into the coding part, right? You do the planning first, and you take actions. When we start to accelerate applications, there are essentially three, at least based on the current, in the context of CUDA and GPU programming, there are three different ways to do that. The first one is based on the libraries. Okay, so the libraries, it's very easy to do. It's high quality acceleration. It's very easy to use. In many cases, you just need to switch the function from function A to function B and then link your CUDA library, and that's it. It's done. That's the easiest way to do the CUDA acceleration or GPU acceleration. And also the quality is pretty good. If your code is already using some, linear library running on GPU, on CPU, you probably can look for some companion GPU version of the library and replace that library, and that's it. You are already getting the benefit of the GPU programming. You don't need to write a single line of CUDA code. And also the libraries are, most of the libraries are released by CUDA, NVIDIA, it's fine-tuned by NVIDIA experts. Those are, highly paid software engineers and been working on this optimization problem for their career. So they are doing a very good job in many cases. And the performance is also almost guaranteed in many cases. So that's a library. I think if you are going to really want to speed up your code, the first thing you do is not to learn CUDA like what you're doing today. Try to understand your problem first, and then see if you can replace part of your libraries just with the CUDA libraries. And that gives you the best performance and the best, investment or return of investment, like ROI. And also CUDA libraries is not small. It's a big library, and the CUDA and NVIDIA, they have been employing, hiring a lot of top researchers and programmers to build this library, spanning from linear algebra and FFT and random generating different solvers, sparse matrix operations, tensor operations, and also the what else? The different solvers, with different algorithms and methods. Highly optimized and highly customized for different architectures. There are different options if you want to targeting the latest GPU. You can make it work better than the previous version, because different versions of libraries will be targeting different versions of the architectures of the GPU hardware itself. For example, this is a very simple library. If you're using, say, as a linear library, SXPY, basically it's get a sum of X plus P plus Y. It's a X plus Y, X matrix, X is a vector, Y is a vector. If you simply replace this function with a CUDA BLAS, which is a BLAS library, SXPY, if you simply replace that library, replace that function call to the CUDA BLAS SXPY, and replace all the input argument from the CPU variables arrays to GPU variable arrays. We'll talk about that later. That's not hard. So you need to allocate memory for those arrays, and then just replace the function call, and finally you link your code against the CUDA BLAS library, and that's it. So you have much less work to do if you are using this library-based method. Of course, if your code has probably, say, 90% of code relies on this kind of libraries, you are blessed. You have a much less work to do, and you can simply replace this corresponding CUDA libraries to do the job for you. Okay. But of course, not everyone is not that lucky. Some of the tools you're developing directly from scratch. You are probably developing brand new algorithms, different numerical schemes. Then you have to probably deal with all this yourself. But for many other programmers, those will be good enough. Yes, so the BLAS is CUDA is a linear algebra library, but I'm not saying this is like one example to showcase that you can do this for many other CUDA libraries. But assuming your current code has a majority code relying on the library itself. Otherwise, getting back to the slide I showed you all, if you only have like 10% of the computation is done by library, even if you replace the library with a CUDA library, the benefit you gain might not be that much. Only when you have a big chunk of computational cost, out of the total cost is offloadable to GPU, then you can benefit from that. So you can get to NVIDIA CUDA tools ecosystem to look for some other libraries that CUDA is providing. Again, it's a big chunk of library. They are providing solutions in different sectors. The one I'm showing a moment ago, those are primary math libraries. Another way to accelerate your applications on NVIDIA GPU is to use OpenSSE. OpenSSE is a standard. I'm not sure if it's an international standard or not, but it's a standard. At least it's a community standard. I believe it's a standard now. So what you do is to insert pragmas. So what are pragmas? Pragmas are like comments to your code. If your compiler doesn't support OpenSSE pragmas, it just ignores them during the compilation state. It doesn't really affect your code much. Not at all, actually. So if you have a compiler that can recognize those pragmas will be serving as tips to your compiler. So it will tell your compiler that this particular chunk of code could be offloaded to GPU, and this is a kernel, and there are, of course, many other different pragma directives like loops, a parallel for, and you can declare your private, public data sectors, etc. So all these pragmas can provide guidance and tips for the compiler to generate code and offload the code using its own runtime libraries to launch the job on the GPU. So this is what's the so-called OpenSSE compilers. NVIDIA compiler by default, the one you download from website or from the CUDA website, won't be able to is not supporting OpenACC, at least for now, as far as I can tell. The NVIDIA HPC SDK has a compiler, which is NVIDIA compiler. The short name is NVC, not NVCC, that we'll be using for today. That one supports OpenACC. The only difference is that you need to provide an extra option called -ACC. It will recognize these options and generates the OpenACC enabled compiler for you. So that's a part that we'll not be getting into details, but hopefully in the near future, there might be some short courses covering OpenACC separately. But today, we'll not get into the details for OpenACC. OpenACC, it's a standard. Again, I'm also sure about the current level of international level or ISO level. I'm not sure about it. But it's a very easy to use, and it's open. It's open for, for community programming, and there are multiple compilers already supporting OpenACC as well. I believe there are GCC also has OpenACC support partially, not the latest full OpenACC 2.3. I forgot the exact model name, the version number, but it provides an alternative to CUDA, so you can directly insert those programmers into your code, either C or Fortran, and you can use OpenACC enabled compilers to compile your code and offload the computing task to GPUs. So it's very powerful, easy to use. The major drawback here is that, of course, is performance and the debugging is pretty hard. If you have some performance bottlenecks, and it's kind of harder to look into the code because it's not, OpenACC compilers doesn't give you the intermediate output that you can easily see and figure out what the generated code is doing. The information from those compiled warning messages, error messages, are also helpful for you to look into the performance user. You have to go to the profiler and try to figure out what's going on yourself. So that's one of the major issues I had when I was using OpenACC myself. But another major drawback is that you won't be able to get the full potential of the GPU hardware if you're using OpenACC, mainly because the way how this memory model is managed, how the kernel got launched, you won't be able to do you won't be able to congregate. I'm sorry, you won't be able to collect and aggregate the kernels and put them all in one big ones, so that you can reduce potential problems. So all this kernel launching and data transfer is handled automatically by the runtime provided by OpenACC. So with that, OpenACC is still a very powerful way for you to explore GPU programming powers before you get your hands dirty on CUDA. Now, the next one, of course, is our programming languages. Programming languages goes beyond CUDA because there are many other programming languages can support GPU programming. As you may have already heard, the OpenCL, there are threads. I'm sorry, that's TTB, and which are able to handle the not just GPUs. I think that depending on the library, particular implementation and the flavor you're using, it's able to handle different devices as well. Thrust C++ template library is one of the libraries that NVIDIA is also pushing hard, which is able to support different architectures, and it's one of the tools that you may want to look into. Mathematica and MATLAB is also providing programming interfaces to use CUDA underneath to generate code that can handle this kernel launching for different computing tasks. Okay. With all that said, I'm not trying to just scare you away about doing CUDA programming. CUDA is still, it gives you the maximum flexibility and performance if you code it right. Otherwise, actually your code could be running slower. To be honest, sometimes in many cases, if you don't do it carefully, or even if you do it carefully, if your application, might rely a lot on the serial, computational tasks, then you might be slowing down, mainly because the overhead you are introducing to copy the data back and from to and from the GPU will kill your performance. So that's a major concern that you'll be dealing with if you want to do the CUDA programming. So we all have this simple example to run some to copy the let me how to we have this simple tasks here, but for today, we are not going to do this interactively on ACES. One of the major reasons is because we have a lot of materials to cover for the CUDA program itself, and also running the job and doing other things. You can learn from other short courses or videos, right? So we are not getting into the part to get everyone familiar with the queuing system and getting your job script ready, etc. So we do have a table that I believe our staff member already shared with you all the link to the example code. These are providing very simple example for you to do vector addition and also very simple unified memory management, etc. So we'll get into details about all the materials, but this slide shows the instruction for you all to get on the ACES code, ACES node, and then module load your CUDA library, CUDA module, and then get your things compiled. So I'll not get into details. I'll use this as an example for you. I'll show you all, I'll go through this quickly myself and show you all how this could be done on your command line interface. And then we'll get back to the basics of CUDA programming first. And after you get one sample figured out, then you can work on your own examples or applications. And then you simply replace part of the job script. You can run your own code easily. So it shouldn't be a big concern for you, as far as job execution is concerned. Oh, this one is already terminated. I can go to my dashboard, go to cluster, and I can have access to my shell script again. I can use a clear, this command line to clean up your screen. Let me see, I should have this under my scratch space. So let me clean up. After you get your CUDA exercise TTD file, this is which is a table, and you can unzip it into a directory called CUDA. So if you take a look at the directory, there is a new directory called CUDA created. You just need to cd CUDA and ls. It will show the example. I'll clean up my screen again. Now, if I do module load or module load, it doesn't show me anything. ML is like a shorthand for module load, ML module load. That means I don't have my CUDA environment loaded. When I try to do NVCC, it returns nothing because it's not loaded. So what I'll do module spider CUDA. It'll print out a list of libraries and for different versions of CUDA libraries that I can use on my computer. Okay. So you can quit this, use a Q. If you do the spider, you can use a Q, click Q to quit it. Or you can just use a space, just to go to the next page, and then you can finish that. So for us, let's do this CUDA. We can do module load. If you double click it, it will automatically copy and paste it. You can copy it to your clipboard. You can just Control V to paste it to your command line and then enter. So this will load the CUDA version 12.6.0. And of course, in the slides, I showed 12.3.2, but it doesn't matter. It's just different versions of CUDA. As long as the major versions are the same, it's not much difference. Then if I do this, I have module loaded here. Then I do NVCC, it shows something. So this is what I'll do. So NVCC -- version will print out information about the NVIDIA compiler, which is already loaded. And then you can also check which NVCC is here. Let me be clear. Okay. Actually, this NVCC is pointing to the one we just loaded. Okay. Now, one thing I'm going to do, I'm going to the CD hello world. I can simply do NVCC hello world set device. Okay. Our front node, the login node, we don't have a GPUs in the front node. This compiler is compiling the GPU code, which could be launched in the computing node. But if you directly run the a.out, this will be running out that print out actually in the front node, which actually is using just the print command. It doesn't do anything. So it's not running any serious computation. It's simply print out the hello world in the front. So kernel launch, it will be more or less like an ignore because there's no CUDA, CUDA runtime there. So to run this job, if you are not familiar with the editor here, you can go to the VI. It's a Linux and Unix editor that you can use to edit your files. But if you're not familiar with that, you can go to the files. You can go to, depending on where you unzip your CUDA files. I'm sorry, I got a couple questions here. So the I'm not sure where. Let me go to the. Guys, I assume everyone should have already downloaded it. You can download this one here. Let me go through this quickly. If you go to the training courses, you have ACES GPU programming here. If you go to view details, the exercise table is here. You can copy the link. You can right click and copy the link. Copy the link address. If you don't have the, I assume you probably don't have that already, you can go to your Scratch space and you can do wget this link. It will download this to you. Another way to do it, you go to your directory. Assuming you already have this table downloaded to your local directory somewhere, to your local computer. And then you can go to the home directory and upload to the home directory. Okay. So this is a file I just uploaded, which is the CUDA library, the CUDA example. So what I'll do, I can simply do, I can so everything else will be the same. The CUDA library will be saved there. Yep. So after you get the CUDA directory, go to the CUDA directory. We have a sample job script that you all can run. If you go to hello world, and again, for those of you who are familiar with VI, you can use VI. If not, you can go to the dashboard where there is a file directory. You can go to your home directory or your Scratch space where your file is located. You go to CUDA. This is the one I just unzipped. Go to hello world. I can click this job script, ACES. I can do edit here. This shows up on my web-based interface. So you can modify the one. So again, this job script actually is loading the CUDA module 12.3.2. This could be, you need to modify it to the same version. Otherwise, you may have some problems with different unmatching CUDA libraries. if you run it. But let me try it first to see if it's working. Otherwise, you'll have to switch to a right CUDA version for that. So what I'll do is this. So what this does is runs this job script and submit it to the Slurm queue system. I'm sure it's. So we have multiple examples running. I just had my queued up here. That's my user account. I'm using queue status. I think there are, this. I'm not. I was a older user of PBS system. That's a queue status. It's the one I usually use. But for S, I think S batch, S info. Let's see. I forgot the S. The Slurm. Maybe. Don't know if it's S. Let's see. I forgot the command line here for you to check your job status, but my job is still queued up. So we have multiple runs with an example. Some of them are already completed. Some users' job is still queued up, but it's fine. SQ-U, okay. SQ the let me see my user account JT1630. I think my job is just done. And let me check my status. I think it should be somewhere. Should be in my. Okay, I'll check back the later, but I'll switch back to the slides since we don't have much time left here. So you need to get the file compiled. You need to compile your NVCC after you load your module. You compile your code and then you get a.out. If you specify the output file, the output file will be the name of the -o output option, like this. If you have NVCC hello world, say device -o my hello, and then the output will be my hello. Otherwise, the default output will be just a.out, which is CC. Nice. And then I can just do S. So I'll let you run, and I'll get back to the slides, and we'll check this later on together. So again, this is just trying to get you all started on the system. And if you have your own CUDA enabled GPU on your computer, you can just run it locally. It's not that complicated. So let's get into the CUDA and C or C++ basics and get into details. So CUDA, the original meaning is computer unified device architecture. But later on, when the CUDA is getting more and more popular and this detailed meaning doesn't really make sense. Everyone just completely call CUDA as a symbol. It's a CUDA. No one refer to the original name anymore. It's not like computer unified device architecture anymore. Excuse me. So the whole purpose of CUDA is to expose the GPU parallelism for general purpose computing. And the CUDA is successful. One of the major reasons is that it's based on standard C and C++. It modified the C++ standard a little bit, extended, but not much. Otherwise, it's more or less like learning a new language now. But for those who are already familiar with C and C++, learning CUDA is very straightforward. It's not very small changes here and there, and the primary difference is actually in the way how the data got decomposed, and the problem got decomposed and launched through the CUDA thread architecture. So the programming syntax is pretty much the same. There are very small changes here, and we'll get into the details. And also the APIs coming with CUDA are very, very useful, very powerful to managing all the things. And it's pretty intuitive to use them. Many years ago, when people started to use GPUs to do some general purpose computing, the only way out is to use like OpenGL APIs, which is highly optimized to do computer graphics and game design. That's what's the primary programming language for those applications. And some researchers, they started using OpenGL to do computation, because even though the names might sound weird when they try to write the code. Well, for example, in OpenGL they use a shader, text, memory, constant memory, whatever. Those are still kept in part of the CUDA context, but the majority of the terminologies got revised into more general purpose programming language like a CUDA now. But still, OpenGL has a very important role to play, had a very important role to play in the CUDA development, in the sense that you might consider it's like it's a formal form of CUDA, but it's targeting graphical processing. In 2007, NVIDIA released the first generation of Tesla GPU, which support CUDA. In 2000, I believe 2009, that's when I first started working on CUDA myself. That's about 16 years ago. So the first stable version of the current stable version of CUDA is a 12.8 update 1 as of April 2025, and it's keep updating because different versions of CUDA will require some update to match the latest hardware development. For every version of hardware, they have different architecture, rough architecture. Essential architecture is the same, but the hardware specifics will be different. So that's why you need a newer version of CUDA to get connected to that. Yes, so change that. I haven't really checked the output, but you can change the version number to make sure it's matching 12.6.0, or you can do the module purge and the module load and use 12.3.2. So make sure it's consistent. Otherwise, you may get some error. I just want to test to see if so this major version, the minor version matching is easy or not. So, but sometimes you may be able to go over it, but sometimes you may get some error messages. So to do the CUDA programming, you need to understand some basic concepts about so-called heterogeneous computing. Heterogeneous computing is essentially combine the computing power of the CPU, which is a traditional processing unit, plus some accelerators. That's exactly what ACES system is providing. It's providing not only GPUs, but also IPUs. What else? We have vector engines. We have FPGAs. And all those devices could be used for accelerating the computing for your tasks, right? So essentially, there are two categories of computing devices. One is defined as a host, and that's defined as a device. In the context of CUDA, host always refer to CPU, device always refer to GPU. Okay, that's there are historical reasons, right? In OpenCL, even CPU could be treated as devices, but CUDA has a very clear distinction between host and device. Okay. So similar to what we talked previously, when you're trying to work on heterogeneous computing, it's always a good practice, always all good practice to have a C version or Python version of CUDA that's already working that you can refer to, and to not only for validation and verification purpose, but also helpful for you to understand the parallelization process and other parts. So in your code, you've probably given the piece of working, say, C code here. This is just one example. Then you can always identify corresponding parallel section or serial section in your main function. The primary task for CUDA programming is to identify that part could be parallelized and use CUDA to rewrite that part of code into some functions. And these functions are called kernels in the CUDA context. And then what your job is to launch those kernels and collect the data from the GPU and finish your computation. Okay, so that's the basic workflow for running, doing CUDA programming. Okay. So for a simple processing flow, you always start with CPU. That's where the entry point is. When you get your file loaded or get some data you want to process, you copy to your computer first. And your computer will handle that data processing with CPUs mostly, unless you have some specialized unit like DPUs can handle data processing. You might also have some other processing power in addition to CPU to handle that. But in many cases, your CPU will be your central processing unit to handle all the tasks that are relevant to your computing problems, right? A simple processing workflow is kind of like this. You have your CPU, you copy your data from CPU memory to GPU memory, okay? And then you load your program from the CPU to GPU. That's where you get your functions or the instructions loaded onto the GPU. And then you launch your GPU program. The GPU program will take the data from the GPU because GPU programs cannot take data direct from CPU memory. So you have to make sure you have your data ready, and then you can launch your instructions. And after everything's done, the results could be returned into the GPU memory, and then you copied all the results back to your CPU for further process. So essentially, it's offloading process. You more or less like shipping your raw material out to the country, process that, ship the final product back to the country. Okay. So everyone knows what I'm talking about. So that's offloading, right? That's offloading the computational processes. This is one simple example. We get started with standard C hello world. This is like very first program everyone's learning. For everyone's learning C, this will be the first program you'll be writing. So NVIDIA compiler can use as a just standard compiler. If you're not compiling any CUDA code or CUDA kernels, it's just work as a standard compiler. You'll compile your code and you can run it on the host without any problem, just like any compiler. So actually, essentially, internally, any host code is compiled by the host compilers. So NVIDIA doesn't have the compiler to deal with the front end. It's mostly using the host compiler to do the compilation. And NVIDIA compiler primarily focusing on the kernel compilation as well as the final linkage. So this is a device code with a hello world. But again, this kernel is not doing anything. It's still empty kernel, but it shows you some interesting features that which is different from the standard C code. So what we have here, we have a global function. Well, it's a double underscore global underscore double underscore. That's a special keyword that CUDA is introducing. That's not something in the standard C or C++. That's a CUDA keyword. Another thing that you might feel like new here, you may see something new here, is the triple brackets here. This is called a kernel launching configuration. And this will providing the configurations about how many cores you want to run and how many, we all get into how many threads you want to launch to run your job. And basically, this main function is just taking your my kernel and then launch it to one thread and then return the control back to the main function. It will print hello world and return 0. That's basically what this main function is doing. So there are nothing dramatic differences. There are some minor difference here. To two differences. One of them is a keyword, global, underscore, underscore, global, underscore, underscore, which indicating that this function is a kernel, is a CUDA kernel. And it runs on the device, and it's called from the host code. That's called a global function. That's when you want to define a kernel that you want to launch on your host, and you want to run your kernel on your device. And that's all these things you need to be aware of, at least for now, because that's the keyword that tells you something different from the traditional C function to a CUDA function. And in this context, we call this CUDA function a kernel. A kernel is something you want to launch with your host code. Okay. So the device function is processed by NVIDIA compiler. That's one NVIDIA needs to convert this into their NVIDIA PTX backend, and then convert that into executables that GPUs can recognize and run. On the host side, the host function, the main function, is compiled by standard host compiler. Could be ACES, Intel compiler, or GCC, GNU compiler. Could be some other compilers, whatever compiler you install on your computer. So does the print? Yes, printf will be printing on the host, because on the device you won't be able to see it. You need to do the synchronization to get the device printed statement C on the host. So you can have a print statement in your host, in your device code, but if you don't do any synchronization, none of information will be getting back to the host. So we'll get into that a bit later when we talk about synchronization, etc. But the print function itself is simply just printing the information on the host. Everything runs on the device needed to be defined in this kernel function. And when the host runs it, it will launch the kernel function, and then the kernel function will do the job. It's essentially just launching a particular function by kernel on the device, on the GPU. Okay. This triple angle brackets mark a call from the host code to the device code. This is just what I just mentioned about the kernel launching. It's a kernel launch action. Compared to the traditional, standard function call, you have this triple brackets. That's the major difference. So 1 and 1 is just a so-called kernel configuration. That's how you tell CUDA runtime how many threads I want to run, and what's the layout of the threads when I try to run my job. And we'll get into that in a moment. So this is all we need to run a function on the GPU, just as simple as that. Okay, you define a function and declare that function with a double underscore global double underscore, and then you define a configuration. The configuration tells the host code how to launch your kernel and how many threads you want to run. So those are the two major components that get your first non-trivial, code working. You can get it compiled, you get it run, and actually my kernel doesn't do anything. But again, this is already a hello world CUDA code that you are actually working. This is the simplest you may have. Now, we want to do some parallel programming with CUDA C and C++, right? So we want to do this massive parallelism, but how can we do it? That's a question. So we'll start by adding two integers and build up to a vector addition. So we want to do a vector addition, vector A plus vector B, we want to get a vector C. So intuitively, given two vectors, if you do this on a CPU, the simplest way to do it is just to write a for loop. You're iterating from index 0 to index n minus 1, you get all your indices iterated, traversed, then you get your C calculated. So you have this sequential operation which is depending on the number of elements you have in each vector, which you should have the same number of vectors. Otherwise, this vector addition is illegal, right? You should have the same number of elements in each vector. ABC should have the same length. So if you do this with a for loop, the total complexity of this problem is just n, because it have to do this one after the other. That's how you write a for loop. Now think about it. If you have this operation inside a GPU, assuming you have a sufficient number of CUDA cores, and each core can take one element operation, then this could be processed with just one clock cycle. Just add, and that's it. So one clock cycle will happen, and each thread will handle the addition all by itself. It just each thread just varies by its own corresponding index. And then all this addition will be happening all at once. That's the parallelism we are talking about with GPU. And we want individual thread, a CUDA thread, to handle individual element inside your vector. CUDA 0 handle index 0, CUDA 1 handle CUDA thread 1 handle index 1, etc. That's giving you a very, very straightforward mapping between the CUDA index and the index of your array. That mapping itself is the most important part in CUDA programming. It sounds like a trivial here for vector addition. Think about matrix addition. Think about matrix multiplication. And think about image processing. Individual pixels could be handled exactly the same way, right? So here, we'll get into the CUDA architecture and show you all how CUDA is doing this, so that you can assign individual arrays element to individual CUDA thread to handle all this all at once, given the very big vector, assuming, your vector can fit into the memory or fit into CUDA cores. Otherwise, you have to do this multiple times, chunk by chunk. But assuming your vector size, it's just say 500, which is pretty small. The CUDA has more than 500 threads, so you can fit in this vector into all the CUDA cores, and only with one addition, everything is done. Now let's get into the programming side. So instead of defining this my kernel, which is empty, we can define a CUDA function, which is AND function. It takes your A and B and give you C. Okay, these are just added to integers, which is fine. I mean, let's just get it started with a very simple integers, and we can do the integer addition. And this AND function will be executed on the device, because this global, remember, this global tells this AND function is a device function. You cannot run it on host. GPU doesn't recognize this function. So it's not defined to be executed on the CPU. It's defined to be on the GPU. Okay. So we use pointers for the variables, and then when you try to do this addition on the GPU, A, B, C, these pointers should be pointing to the GPU device, not the CPU device. Only by doing that, the GPU CUDA cores or threads or hardware can grab the data from the GPU memory. It doesn't see anything from your CPU memory, at least for now. I mean, so far, it sees nothing from the CPU memory. It can only see the data from the GPU memory. That's why you need to allocate memory on the GPU to do that. So before we start getting into the programming, we needed to look into some very key features for CUDA, the memory management system, which actually plays a very important role when you're doing optimization, doing any other CUDA programming. So we all know that device pointers pointing to the GPU memory, host pointers pointing to the CPU memory. So host pointers is just standard C pointers you have been playing around. And the device pointers are the new ones we need to learn how to allocate and how to deal with those. CUDA API is providing functions like CUDA malloc, CUDA free, CUDA memcopy to handle the GPU device memories, just like malloc, free, and memcopy from the standard libraries. And if you're familiar with the standard libraries, stdlib.h, those libraries providing memory handling for standard C programmers, right? So, okay, it's easy. So we have a different system of memory management. It's just CUDA malloc, CUDA free, CUDA memcopy. We can do the same thing. But fortunately, NVIDIA is, of course, they have very smart engineers over there. They have been facing exactly the same problems for memory management. So they started supporting so-called unified memory in CUDA 6.0. Now we have CUDA 12.0. It's like, many, many years ago. It's 11 years ago, 2014. That's when the first unified memory got supported by CUDA software. In 2016, like 2 years later, Pascal CPU, which is another older generation of the GPU architecture, started supporting this unified memory on the hardware level. When they're saying in the hardware level, it means that there are special hardware mechanisms designed to make this unified memory process faster. That's what they mean by hardware support. So it's not simply a software algorithm kind of like processing. It have a hardware to detect any memory access for the unused memories, and then they'll give you a petafort. The petafort will trigger some other actions, etc. So those have hardware support, which is much more efficient than doing the software, checking for the unified memory, etc. So what is a unified memory? Unified memory is providing some virtual memory space that is managed by CUDA. You don't need to worry about it. So all you need to do is to, instead of do the CUDA malloc memory array, you could do a CUDA malloc managed. So it will make sure that a particular chunk of memory is managed on your GPU. And the CUDA is allocating the CUDA will be allocating the corresponding memory for both CPU and GPU. And whenever you have a CUDA device synchronization function is called, it will copy the latest update on either the CPU or GPU to the one which was not updated. So it will synchronize the data, give you the latest data on both CPU and GPU. So unified memory give you a much better way to handle your memory information, handle your data inside your memory, either GPU or CPU. So you don't need to do the mem copy anymore. But when you get started learning CUDA, very first thing you learn is to copy data from CPU to GPU, GPU to CPU. But now with the unified memory, this could be completely removed. You don't need to do the mem copy. You just need to do the CUDA device synchronization. It will copy the data accordingly, depending on which direction it's copying into, depending on which data you have, which part of the memory you don't have the data, which part of memory you have the data. So make your code much faster, much simpler, but not necessarily faster, but much simpler. Okay, that's a unified memory. Now let's get back to this. So return to our add function, and let's take a look at the main function here. In the main function, we have the host function, which is we need to define host copies of ABC. It's just 3 numbers. Okay, 3 numbers, and then we define the device copy of the ABC, and then we allocate space for device copy of ABC depending on the size. It could be, size could be 1, could be 2, could be 1,000, and we want to allocate memory on the device. That's something we need to do. But this one doesn't do the unified memory, and we'll learn how to use that later on. There are some examples to do that later. So let's set up our input value, A and B. We want to calculate C, which is A plus B, okay? So what we do, we copy the data from A to DA size here. Of course, if it's just one number, if it's just one, if it's a vector, it will be a vector. So we're copying data from the host device. So I'm not getting to unified memory yet. This is still manual copy. Even though there is a unified memory, but in many cases, many programmers prefer to do the manual control of the copying because you might have some extra gain in the performance when you're trying to try to parallelize the data copying and the computation. And that only works when you have a manual controlling of the copying process. Unified memory is usually done automatically, which sometimes might not give you the maximum performance. So this is why we still probably want to get ourselves familiar with this manual copying. So the CUDA mem copy host device, this is just a flag, like 1 or 0. If it's a host to device, it's probably just one number, and the device to host is another number. So when you need to copy your data from host to device, you need to put a flag there. By doing that, you can keep the same function name unchanged. It only changes the flag. The flag will tells the CUDA runtime which direction it's copying to. And then next, you launch your kernel, DI, DB, DC. Remember, DI, DB, those are already GPU memories. DC, these are all allocated on GPUs, depending on the size. Here size is just 1, it's a no big deal. And then you can do the mem copy back from device, from C, from the C's memory allocation on device to the C memory block. That's from the device to host. So that's how you get your results back. That's where C is. And then you can free up your A, B, C. Of course, you want to do some print out your value and double check your results. That's something I didn't include here, but again, that's basically the workflow. Now let's move from one variable to one element to multiple element in a vector space. So we want to increase the number of threads that we want to handle. Here, we simply change this n, 1 to n. And I'll explain why I changed this one instead of the other one, but it's essentially the same, but there are some differences. So that's something I want to emphasize a bit later on. So here, what this one does, it's trying to launch this add function n times in parallel on n CUDA cores. So each CUDA core will take this add function and launch it and run it in parallel, all at once. Okay, so we're not running this on one thread anymore. We're running this on n threads, all at once. Okay, so that's a major difference between our previous one because we are already changing our kernel configuration. And our kernel, depending on how you write it, your kernel, you don't need to modify a single line depending on how you write it. And of course, if you write it in a noisy way, you probably want to modify your kernel. But if you simply want to increase the processing of number of elements, this is all you need to do. The same kernel will be launched across multiple number of threads. Now let's look at this vector addition example. Assuming now we have A, B, those are vectors, and C, those are all vectors, not just single numbers anymore. Okay. This add function will be not simply A, star A plus star B equals star C. We have a very special new thing to introduce here. It's called a blocks index.x. Okay. So what this one does, block index.x is a constant when the job started running on the CUDA core. So given the CUDA core, assuming you have 100, you launch your code on 100 CUDA cores. So for each CUDA core, there will be a local index given for this kernel launching. This block index.x will be referring to the corresponding index. First core will have block index.x equals 0, second one will be 1, etc. So even though multiple cores, CUDA cores are running the same function, but the element of the vectors that you are processing will be different because of this block index.x. This block index.x is a runtime constant. It's not a variable, it's a constant. When the kernel is launched, this block index.x will be constant for the given CUDA thread. Because the number of CUDA threads is n, and the particular index for the individual thread is a given. That's something already given by the CUDA runtime. So this block index.x is a fixed, is a number. Just you can consider it like a constant for a given CUDA thread. It will be replaced by its own index. That's why even for the same function, but for individual cores, it will be using different element of the vector, mainly because of this block index.x. Okay, this is the most tricky part for new CUDA programmers. You are launching the same function. It's this index that you calculated will help you to find the corresponding element that you need to process automatically without you doing anything. Because that's what you put in this function. It's handling the corresponding index, right? So look at the last sentence here. By using this block index.x to index into the array, each block handles a different element of the array. Now let's look at how it works. So in this function on the device, so each block will be executed in parallel, and each CUDA thread will be handling each block here. Okay. And block 0, which already will be fixed, it's a given. Given a list of blocks, and I have 0, 1, 2, 3 already there. It's already put on top of my head. I have block 0, that's me. And another one has a block 1, that's him. And given that number, it directly goes to the particular memory address to find the corresponding element. The numbers, if you call the same. Yes, so in this case, we'll get into details. This is just getting everyone started. We'll get into details. We needed to handle the arbitrary number of indices because the total number of cores, number of blocks, they are fixed. You know, there's no unlimited number of CUDA cores you can use or CUDA blocks you can use. But there could be an unlimited data you need to process. We needed to handle that separately. We'll get into the details and to make sure that we can do that. But for this example, I just want you to see how this mapping is done inside the CUDA. I'll now return to our parallelized add function, and that's essentially what this block is doing. The only difference is that we are not simply adding B and C to A and B to C, we are adding the corresponding element of B and the corresponding element of A to the corresponding element of C. That's what we are trying to do. Now in the main function, A, B, C are still the same. There's a host copy of A, B, C. Those are not numbers anymore. Those are vectors. And we are going to allocate memory for them. First, we allocate device memories at the top. That's malloc. CUDA malloc is allocating device memories. The size is simply 512 times the size of integer, which here it's, for example, 32 bits. It will be 4 bytes. And then you can just allocate that many bytes for the device memory. You allocate exactly the same for the host memory, right? So we're not doing unified memory allocation yet. We'll learn how to do that later on. So next, I randomly initialize A and B, given the number of n, A's and n B's. I randomly initialize them with random number. This random init is just an initialization function. I just basically setting, A and B values randomly, just for testing purpose. Okay. So far, so good. We have variables declared, device variables. all those, remember, all those device copies of ABC, those are at this point, before we start allocating memory with a malloc, those are still local variables for your host. But then when you start allocating memory for DA, DB, and DC, they'll be pointed to the memory address, pointing to the memory address of all the GPU memory blocks. Okay, that's when you start making this DI, DB, DC special. But when you declare them, in the first two lines of this main function, they're just like a regular declaration of pointers, nothing more, nothing less, nothing special there. But when you start allocating memory, it will give you this special pointer that DA can point to a special memory address, which is actually inside the GPU memory range, not in the CPU memory range anymore. It's just different scope. So DA is like pointing to somewhere on moon already, and A, B, C are still pointing to somewhere on Earth. It's just like a different space you're talking about. So all the operations underneath is like for A, B, C, those are host code. There's nothing about GPUs at this point. Now, next, what we do, we copy the data from A to DA, B to DB. Remember the diagram I showed you all, we first need to copy the data to the GPU memory. That's exactly what these two statements are doing. And then next, we launch the kernel. So this kernel launching is copying this kernel function. Kernel itself is a piece of code. A piece of code is a piece of data. This piece of data needs to be copied to the instruction side for the GPU, to launch it, right? So you copy add function, this kernel, onto the GPU memory, and then run this add function n times. N is 512. So 512 times at once altogether, because, assuming we have sufficient, we're getting back to a larger problem size, but assuming you have 512 CUDA cores, so each add function will do its job in its specified CUDA core, and each specified CUDA core has its own index, goes from 0 to 511. That's when you call this add function, it will do this addition for individual CUDA core, just one cycle, one add. All the cores will be executed. All the add functions will be executed on individual cores, then you get the results calculated and saved in your DC, that's in your GPU memory with n blocks. And after that, you copy your data back from DC to C. And you can see the flag here, CUDA memory copy from device to host, and that's it. And that's it. You can then take this C as your result. You can do analysis, you do anything, you can print it out, you can do whatever you want. Okay, this is the whole pipeline for doing this vector addition. I demonstrate how this CUDA kernel is launched, the data got copied, and also finally you need to clean up. You need to free your ABC, you need to free your CUDA ABC. CUDA free is freeing those device memories. Remember, ABC, these are pointing to CPU memories. That's why you need a CPU free function. And the CUDA free DIDBDC are pointing to GPU memories. You need a CUDA free to free them. Okay. It's pretty clean, right? So far, so good. But the tricky part of getting into this kernel configuration and the kernel function, that's the tricky part. Before we getting more complicated, starting talking about grid hierarchies, etc. Let's first look at the unified memory that we talk about, which is something that I think everyone wants to learn a little bit about it. So in this vector addition function, I'm doing something a little bit different. For this return value, I'm not directly using the vectors A and B. I'm just using some value you give to me, A and B, and I add my block index to it. It's just, again, like a random calculation. It doesn't mean much, but just A plus B plus my block index. Okay, and save back to my block index. It's exactly the same like what we did before. It's just like my calculation is a bit different. So look at the main function here. I allocated memory for my return value, which here I'll I need a GPU memory because that's a part I want to modify on my GPU. So it's 1,000. That's the total size of this vector times size of t. That's giving me 1,000 integers on the GPU as well as the CPU. So it's a one variable. I don't need to declare if it's a D or D return or return. So it's just return. It's just one variable. Have two copies of data on both CPU and GPU, handled by the CUDA unified memory. So then I just simply launch my function, launch my kernel, and take my return value and just take this 10 and 100 as my A and B. Remember, A and B here are not vectors. Just I want to make this whole code easy to display on one page. I don't want to allocate memory for my A and B doing other things. Just simply use A and B as numbers. I can do this vector addition on 1,000 CUDA cores, and then and do the calculation. And then I do the device synchronization. The data will be automatically copied back to my CPU, which is quite nice, right? And then here, I actually have extra loop to print out the results, and you can see the results here. Okay, so again, actually this, if you look at this example, the output actually, the printout statement might not look correct because I add extra block index. The main purpose is just to show you it's actually not exactly A plus B because I have an index there, index.x there. And then you can see the difference. You can modify this code and play with it yourself. But this is a fully functional CUDA code. And utilizing CUDA, a unified memory management system, and it's able to print out the results back to you. And again, it's already a non-trivial CUDA program. Of course, NVIDIA, they are providing some other extra functionalities that for this managed memory. One of the things that you might be using, because CUDA kernels usually in these CUDA programs, it's usually has a dedicated memory blocks. So it's pretty common, for certain CUDA applications to use so-called global GPU memory to store the data in your GPU memory and everyone else can have access to. If you are C or Python programmer or Java programmer, people may tell you that don't use global memory. There will be security concerns, etc. So again, it's the same here for CUDA. It's not everyone is recommending the global memory, but it gives you some quick, demonstrative stuff running and get you started quickly. Just for practicing purpose and for certain applications, global memory might not be a bad idea. For example, here, you can define a GPU memory using device. Remember, global is to define a function or something on the device, but launchable from the host. Device is define everything on the device. Host, as you may imagine, I don't use a host here, but you may imagine there will be underscore host underscore, which device everything on the host. But again, that's only help for you to distinguish. But essentially, if you don't put anything there by default, it will be a host definition anyway. So underscore device underscore will define a global memory block, which is a return with 1,000 elements. And the managed keyword tells that this memory block is a managed memory block. So it gives you a managed global memory, which is very, very nice. As you can see here, you don't need to do any memory allocation, and then the synchronization, other things will, it's still the same, but you just need to define this managed memory block at the top, and that's all. That's probably, I would prefer to write my code this way if my application does, need access to a global, array at some point. This gives me a very readable code and make my code, much cleaner. Okay, so this is another way to use global memory because memory allocation is very important. So I already mentioned about some non-trivial examples. And next, I'll get into so-called grid hierarchy or CUDA thread hierarchy to show you all the meaning of those numbers, and I put in the triple brackets. 101, what does that mean? How to use them, etc. Actually, you can put up to 4 parameters here. We're not getting into extra 2. One of them is about streams, another one is about shared memory size. We only use these 2 here. We only use 2 numbers in the triple brackets in the context of this short course, but you can learn more about those later on. So what's the hierarchy of the threads that we are talking about here? In the CUDA programming abstractions, there are 3 key extensions compared to C and C++. The first one of them is the so-called hierarchy of thread groups. We'll get into the details about that. It's more or less how you organize your threads into blocks and how you organize your blocks into grids. And then when you launch your kernel, you'll need to provide a so-called grid configuration or thread configuration or grid configuration. It's mostly grid configuration. And the numbers, 2 numbers, is describing how you configure your grid. We'll get into details. The second abstraction is shared memories. For those who are C programmers, you know C is very powerful, right? C can give you access to all the memories, to pointers. You can go anywhere in the system as long as you have an address. You can go there and modify and do something, right? It's kind of Hanker's favorite programming language, C. Now, but in the traditional CPU programming, you don't have any control over the cache of your CPU. The compiler handles that for you automatically. Okay. But in CUDA, you were given this capability to handle all the cache for your calculation and computation. That extra power gives you extra freedom for further optimization, but makes this programming another level of complexity got introduced by giving you the freedom to do the shared memory programming. That's something we don't have time to get into. That's probably next, CUDA intermediate or advanced topic, get into shared memory manipulation. And to give you another memory hierarchy, consider we starting from, say, hard drive. That's the storage, very low latency, very high latency, low bandwidth. And then you have a memory, CPU memory, and then you have L3 cache, L2 cache, LRAM cache. Every layer of this memory give you a hierarchy of memory structure. That's called a memory hierarchy. So shared memory is getting to the L2 cache, L3 cache level for the GPUs. So the GPUs can give you access to this shared memory for you to further optimize your code. And again, we will not talk about the details of shared memory programming in this short course. The barrier synchronization gives you the freedom and give you the power for you to do a synchronous calculation and as well as make sure that you don't have any racing conditions, etc., and provide a barrier for your thread system. So essentially, it's a multi-threading system, CUDA. But CUDA has a very lightweight thread management and launching schemes. But of course, someone from DeepSeek might not be agreed. They may figure out, say, they are telling NVIDIA that their current launching schemes might be too expensive. We might read some paper from the DeepSeek developer teams about their kernel launching strategy. They modify the PTX code and to make the kernel launching much faster. But again, that's not the concern for today. But compared to the traditional P threads and other threading libraries and frameworks, CUDA threads is much lightweight, and it has a hardware support. So it's a very, very efficient. It's about nanoseconds level of efficiency, talking about microseconds efficiency for some other applications. So it's very, very efficient to launch, kill, and manipulate CUDA kernels. I'm sorry, CUDA threads. So this barrier synchronization will enable CUDA to leverage this advantage of this CUDA-based threading, multi-threading library to produce all kind of different application scenarios that you may imagine. So that introduces another abstraction that we can leverage for us to launch kernels and stream and do the dynamic parallelization, etc. There are some other things you'll learn later on. So what is a thread? Thread is an abstract entity that representing the execution of the kernel. Each thread is referring to each virtual CUDA core, and it's just run very efficiently. In most cases, each thread handles individual element inside your vector and matrix animation, matrix operation. So thread can always, refer to the smallest computing unit that you use to do your computation. Okay, that's a thread in the context of CUDA here. So grid is a collection of threads, and threads in a grid execute one kernel function. So when you provide the kernel configuration, that's essentially describe what this grid looks like, and how you want to launch your kernels across the whole grid. So each kernel, each grid, one kernel, one grid. Okay, so that's something you want to be careful, because when you do the multiple streaming CUDA programming, you can have multiple streams. Each stream is very similar to each queue inside our high-performance computing systems. And you can keep launching kernels, and the kernels will be queued up because this particular queue or particular stream doesn't have sufficient resources for you to run this kernel, right? To run multiple kernels all at once. So it will ask you to just queue up in this particular stream. So each kernel you launch has its own grid attached to it. That's your configuration. This configuration could be dynamic. Depending on your problem size, you can change the configuration to match your problem size. Okay, that's exactly the part of the kernel configuration that we needed to look into in a second. We should still have time. So thread block is a group of threads which are executed on the same multiprocessor, which is something many people got confused now. You talk about GPUs, I understand. It's a big, gigantic, socket with everything on it. That's a GPU. That's a GPU socket, right? Now we talk about multiprocessors. What is a multiprocessor? So multiprocessors are you might consider these are GPU cores compared to CPU cores. This cores has a shared memory, which is the shared memory that everyone can have control to. You can utilize the shared memory. This shared memory is kind of like L3 cache shared by multiple cores inside your CPU. But each multiprocessor has its own shared memory, which actually gives you another interesting level of complexity in handling this, because you need only not, when you really want to maximize the performance, you not only you want your thread to be running, but you want your thread to be running as close as possible on the same multiprocessor, right? And that is another thing that we will talk about, actually. So that's a threaded block. So grid is constructed of multiple threaded blocks. Each block is constructed by multiple threads. So it will be grid, block, threads. That's the basic hierarchy we're talking about. So with multiple threads, we can build different blocks. Multiple blocks, we can build out different grids, and each grid will be attached to individual kernel for the launching. So this could be in 1D, 2D, 3D. You have your grid could be, your block could be lined up as a cubic in your grid, and your thread could be lined up as a cubic inside your block. And then you have a grid with a three-dimensional blocks and a block and three-dimensional of threads. You might consider this like a 3D tiles you're painting up to fit into your grid. Okay. all these are talking about the virtual setup that you're making. So physically, you may have limited number of threads per block, but this virtually you can have pretty big number. So number of threads per block and the number of blocks per grid are specified in these triple brackets. Now we know these two numbers are. The first number, that's the 1,000 I'm using, it's the number of blocks per grid. And the other one, second number you have, is number of threads per block. Okay. Now, getting back to probably some of your previous question, why do we use the first number instead of second number? Because the first number seems not referring to the individual threads, it's referring to individual block. The second number refers to number of threads per block. Why don't we run the example previously with, with multiple threads instead of multiple blocks? The reason is that there is a physical constraints about how many threads you can run per block. So the second number you have there is an upper limit, which is up to about 1024 for certain dimensions and much smaller for some other dimensions. So 1024 is the maximum number you can put for the second dimension, for the second number. Now for the first number, the number of blocks, it can be up to billions, because that's virtual, right? Virtual blocks you can construct. You can have billions of virtual blocks, and each blocks could be handled separately, and the grid structure will just queue up all the blocks into a virtual grid structure. You can submit it, and the job will be launched block by block, and without any problem. If you have multiple blocks, in your job script. I'll get back to the real numbers in a second. You'll see what I meant later on. So for each block, it has a block ID. Okay, and the block index here has 3 dimensions: block index.x, block index.y, block index.z. That's representing 3 index to construct your final grid. And the total size of blocks inside the grid is called a grid dimension. That's on the grid side. Now, if you look at an individual block here, I'm just at the bottom. This graph, after this figure, you see a block 1, 1, which is here. I'm just talking about 2-dimensional block. I don't get into Z dimension, just X, Y dimension. I have block 1, 1 here. Block 1, 1 here has how many? Have like 1, 2, 3, 4 along X and 1, 2, 3 along Y. So we have 3 times 4, threads for my block. And the block dimension refers to the number of threads per block. Here, the block dimension is different for X and Y. The block dimension X is 4, block dimension Y it's 3. So you are building this block of threads. Okay, so this is how all the threads got organized internally. Now, getting back to my original comments about what CUDA is. CUDA programming mostly is about mapping all these blocks indices and thread indices and grid indices with your particular element indices. That's, if you get that one done, you get like probably at least 50% of the work done. Being able to map this properly without missing any element, that's already a big achievement, actually, for beginners. The second one is to make sure you check the boundaries. You're not referring to the boundaries, your index is not running out of bound. That's another achievement, right? The third achievement will be about the performance. How can you utilize this grid structure and maximize the number of threads per block, mainly because all the blocks are sitting in the same, SMX, the multi-processors. So you can utilize the shared memory as much as possible. So that's the level 3. Level 4 will be getting to utilize the shared memory. Let me get into the utilize shared memory and then try to maximize the locality of the data you copied to the global memory and GPU memory and shared memory. So the question is the topology of the inter-block and inter-block communication inherent 3-dimensional is just synthetic? the synthetic sugar to access to the linear continuous. That's a very, very good question. Actually, there's no intercommunication. You don't send messages. That's a difference between if you are communicating with MPI processing, right? You do the message passing. Individual process, they can send a message to your peers. But for this, everything is done completely independently. You either synchronize, copy data, or you don't do it. So there's no communication when you're launch this kernel. So all the threads are supposed to be guaranteed to do its own job without any interference until it's done. So you don't want any communication between internal threads or internal blocks. So getting back to your question, I think you can treat it more or less like a syntactic sugar for you to I didn't use that. Yes, so inside each thread block, you have a shared memory, you have access to the same data, but you don't communicate. Individual threads that don't communicate. You have access to the memory, but when you run your process, you are completely independent. When you use a shared memory, you can have access to the data much more efficiently than the global memory, but that's a major benefit. You don't communicate. The only way how you communicate is to do the synchronization. That's you want to make sure all the data on the shared memory got synchronized. You don't need to, don't have multiple threads co-writing everything. But when each threads are running, they're completely independent. That's actually the main difference between the P threads and traditional threads, that you have mutex and other things to make them talking to each other. But in the CUDA threading framework, individual threads are completely independent, and you don't want to interfere with that. Actually, that's actually one of the main reasons why the performance of the CUDA threads are so good, because you, by design, you need to make sure that individual thread needs to do its own job. Okay. Now, these are 3D. When you have 1D, it's relatively straightforward. 1D thread, you can just use the index as a thread. When you get to 2D, then you have both dimension X and Y, and then you need to multiply the dimension of that. More or less like someone give you a 2D index and ask you to create a 1D index for the 2D array. How do you do that? You multiply depending on it's a row measure or column measure. Consider, since we are dealing with C, it's a row measure. So your dimension X is essentially how big, how wide your matrix is. And then the total index is essentially the X plus Y times block dimension X. The reason is Y is like a number of rows, and the block dimension X is the total length of your row. And then your total global index is essentially X plus Y times block index X. That's how you convert this two-dimensional gradient size into one-dimensional index for your array if you need to do that. You can do the same for the three-dimensional index. Okay, so this is how things getting more interesting. How do we index arrays with blocks and threads? Assuming we have just one-dimensional blocks and one-dimensional threads. Okay. Consider we have an array with one element per each thread. Basically, we have 8 threads per block. Okay. That's, you can put in your configuration. You want your second number to be 8. That's 8 threads per block. The first one is number of elements you want to put in there. So look at the index here. I have thread index, which goes from, for the first block, it goes from 0 all the way to 7. For the second block, which is the block index dot x equals to 1, my index is always local. Remember, all the indexes are always local to itself. So the thread index goes from 0 to 7 for the second block, the same for the third block and third block, last block. Okay. Now, if I want to calculate my global index, if I want to count from all the way from left to the right, I want to find my corresponding index for if I want to map this to my one-dimensional array, what is my index? My index is simply the thread index plus the block index times block dimension. The block dimension is what? It's 8. It's a constant. Given the configuration when you launch your kernel, all these are constant. You can always get these numbers calculated, without any extra overhead. This could be done during the compilation stage, right? Okay, let's look at this particular example. I have this array going all the way from 0 to 31. That's 32 element. I have 32 element array. And these are just referring to the index for my array. It's not referring to value. Value could be dramatically different, containing different values, right? Here, I'm just referring to the index on my array. So now I want to see which particular thread, which specific thread will be operating on my red element here, which is number 21. How to do that? The math behind it, simply you'd use this 21 divided by the block dimension, which is 8, right? Block dimension is 8. So you have 2 times block dimension, you get a 16. Then you have extra 5 left. It will be 5 plus 2 times 16. Does it make sense? If you look at the bottom row is exactly the same as the previous row. Yes, that's good. So someone's following me. Good. That's very good. So bottom row is the same as the one I showed in the previous slide. I have dimension 8, and I have block index, which is given. For the given block, the block index is a constant. And I have a corresponding local thread index. So to find the corresponding construction of my block configuration, the thread index is 5, block index is 2, and the block dimension is 8. And that's how I got my 21. Okay. Now let's try to do something more non-trivial, and it's more relevant to the final task for today, is to handle an arbitrary vector sign. If you can do this already solves a big chunk of problem, because not everyone's dealing with matrix, right? I mean, I know many people are working with matrices, but many of the problem could be easily handled by the one-dimensional vector. If you can do this arbitrary vector operation on GPU, you can already solve a big chunk of problem. Even though that's why even this vector addition looks simple, but it's already representing a big chunk of problem. I would not say like 1/3, probably actually 1/10 of problem that you might be facing could be solved by simply modifying this kernel function and kernel launching. Okay, so most problems are not friendly with multiples of block dimension x. Your block dimension, if it's 8, for the previous example, it's 32, it's a perfect matching, it's fine. But what if your total problem size is 501? And your block dimension, for example, is 16 or 32, which is commonly used for many other considerations. I'll talk about that later. Then you cannot easily equally or wholly dividing that 32 by 501 by 32, right? So there are always some extra thing left. How to deal with those extra items so that you can make sure all your element could be handled by your threads and blocks. The vector addition part here, nothing's different. The only difference here, look at the particular element statement here. Index, I do the calculation exactly the same way I calculated previously. It's fine. And then there's one extra statement, index less than 10, or less than total number of elements. This will guarantee that you will not go out of bound. If you go out of bound, you need to access to the memory that is not assigned to you. It's a violation of memory access, and you get an error message. Sometimes you get a segment fault. So this will check. Look here. This is check for individual thread. Every thread will be running this function, we're running this kernel. So this conditional statement, it's running, it's executed, it's evaluated for each thread. If you want to run 1,000 threads, this if conditional statement is running for each thread. So for each thread, it will try to check if the current index that calculated based on my own index, thread index, block index, and block dimension is less than n. If the index is less than n, that's okay. I'll do calculation. Otherwise, I don't do anything. So my C index initialized by zeros, this value will not be touched. So those negative values probably still negative values. I wouldn't touch them. But you can do error checking later on. When you copy the data back to your CPU, you can say, okay, my initialized C is always equals to negative 999, and it's not touched. So probably, that's already the boundary, etc. Okay. But that's when your C has some larger dimension. But in most cases, your C has a dimension of n. So you should have everything handled properly with this conditional statement. So this is a boundary check. It's already solving a big problem. And the first statement about index calculation already get you the index mapped. Okay, this global function is already working for your vector addition perfectly well. Now the next thing is how to handle that for your kernel launch. The global function can do this individual thread operation properly, but how can I launch that to maximize my benefit, to make sure that all my GPU cores could be utilized, right? So assuming you have arbitrary vector size, the kernel launch, the number you do is you first give block dimension m here. This m could be any number, technically, could be all the way from 1 to 1,000, I'm sorry, any number up to 1,024 for one dimension. Because as I mentioned, the maximum number of threads per block can only go up to 1,024. So m could be any number between 1 and 1,024 for one dimensional. Two dimensional is different. You have different dimensions. The numbers are different. Now, as I mentioned, all the threads inside the blocks, they share the memory. And there is a very special number called 32. That's by design. That's what CUDA, it's NVIDIA's decision. It's not my decision, right? The 32 is a CUDA's decision when this first designed this architecture. So what they did, they have 32 threads called one warp, W-A-R-P, warp, to share the same memory. So technically, it's always a good idea to set this M, capital case M, like a number of threads per block, as a multiplier of 32. Then you don't have so many choices, like 32, 64, 128, whatever. You have those numbers there. Thank you. So we all have this recording. If you want to go back, we can always, check the recording. Given this M, the other could be simply calculated based on this M. This number of blocks per grid will guarantee that you have barely sufficient number of blocks to cover everything. You don't want to waste extra blocks here. That's why this very interesting, special numerical, mathematical, not math, algebraic equation is here, not equation, the expressions here. N plus m minus 1 divided by m will give you the integer, which is the ceiling of this operation. Basically, it's give you something 1 plus n minus 1 divided by m. If you m divided by m is 1, right? 1 plus n minus 1 plus divided by m give you another thing. Wait a second. It's I'm sorry. N plus m minus 1 divided by m will give you the minimal number of blocks to cover all your n elements. So you can do this yourself, but I don't think I can explain this as clearly as possible unless you do some examples yourself. So you can also call the function ceiling and ceiling m or ceiling n divided by m, etc. So ceiling n divided by m, then you can get the number. So this configuration will guarantee that you have sufficient number of blocks to cover all your elements, and you'll have sufficient number of threads per block to give you the best performance. So this is how you handle an arbitrary vector addition, multiplication, and other operations. As long as you have a 1D array that need to be processed and handled, this could be used as a template for you to work on it. Okay. So now, why do we bother with the threads? I mean, it seems to be adding another level of complexity, and why do we need to do? What do we gain? So why do we need a thread here? Threads provide within a block, it's providing a shared memory through the shared block with the shared memory. As I mentioned, it gives you another hierarchy. If you want to do some tiled operations, for example, if you do the matrix multiplication, you can do the blocks multiplication with different blocks of your tile. Then you can copy the data of that block into your shared memory, and you can reuse that multiple times. By doing that, you can compensate the time for you to copy data from global memory to shared memory by minimizing the memory access needed to the global to the GPU memory. Right. So shared memory here is a shared memory of the CUDA cores. I know the GPU memory is already fast enough, very fast. But if you need to access every individual data for every element, then you have some extra overhead to consider. And copying this data in a batch mode will be much more efficient because every batch you can copy a lot of data together. If you copy just one element, it's not so efficient. If you copy a batch of data together, it's just one operation as well. But this batch of data could be reused. You don't need to go back and forth, copy multiple times from the global memory. So the latency between the shared memory and the global memory, the difference is about 1 or 2 orders difference. One of them is about 10 nanoseconds level. Another one is probably 10 to 100 nanosecond level. So consider that's the order of difference in latency when you try to have data from either shared memory or global memory. So the threads inside a warp can have access to this shared memory, can have a very fast access to the data needed, and can maximize the performance naturally. So the shared memory could have some issues if the data is not synchronized properly. So the sync thread is used to share with the shared memory synchronization. And again, we don't have time to go into the optimization for shared memory, but if we are dealing with the matrix application and image processing and many other operations that might be using the same group of data, neighboring data, not the further away. If you are using the same group of neighboring data many times, this shared memory optimization will be needed if you really want to get the full performance of your CUDA program. So next, I'm sorry, we have about 20 minutes. I think we still have some time to get back to the example. I show you some demos there. But next, let's get into the devices, because in many computing nodes, you have more than one devices, and it's in many cases, for example, in ACES, you can do a GPU programming with up to 16 devices, 16 GPUs. Just consider how much power you may have. But the thing is that not like some other, very specialized architecture, the ACES system has 16 GPUs working separately as individual devices. They have their own device ID. So you needed to figure out a way how to divide your task onto different devices so that they can do all the work in parallel, right? So the kernel launches are synchronous. So whenever you launch your kernel, the control will get it back to the next step in your host function. So, and then the CPUs needed to synchronize before consuming the results. You can do the CUDA memory copy and synchronize, and you can do the device synchronous so that you can block the CPU until all the GPU calls have completed. That's how you coordinate the host and devices. Now, I'm sorry, where is it? Okay, I'm sorry. So before you get into the device management, there's another part of the thing that I think is needed for you to all learn how to utilize it. It's called error handling in CUDA. CUDA has a CPU, APIs that have a very clearly documented error code as well as error messages that can help you debug your problem. Sometimes if you cannot allocate memory because it's running out of memory, or could be some hardware failure, etc. So it will give you some information about whatever error you are encountering. And that's the CUDA error data type is trying to help. So for every CUDA error code, you can find the corresponding strings describing the error message. So this could be utilized with the CUDA error function APIs. And again, these are something CUDA is providing, and you cannot find this in any third-party libraries because that's CUDA's library, and CUDA providing this error handling. The best way to find the corresponding errors for the particular, CUDA programming issues, utilizing this error APIs will be very helpful. Okay, let's get into the devices. So we mentioned about handling hosts and devices. You need to do the synchronization, before everything is done by device to make sure everything is ready before you copy all the data back to the host, right? That's when you're handling host and device. Now, assuming you have multiple devices, the way to do it is kind of similar to MPI in many, many ways. So MPI, called Message Passing Interface, it's a programming interface or standard for people to write massively parallel programs, right? So there is a MPI communication word, communication word, communication word. I think that's basically what it is. So that's more or less providing the context, providing all the metadata information about how many processes you're running, which process you are on, etc. So the keyword in there is called a rank. You have a rank 0 all the way to rank n-1. N is the number of MPI processes you're running. That's for MPI job. Now look at this device management function calls. It's providing something very, very similar to that. So CUDA get device count give you a total number of devices you have on your given computing node. And get device or get the particular device index. It's very similar to rank ID that you have when you have MPI code running. And then you have a set device. This set device for you to set particular device when you want to launch your kernel and create other streams or other things. So that's specify a particular device you want to do certain things. So assuming you have a pretty big array you want to handle and want to run on, say, 4 GPUs in your node. So what do? You cut your total memory, total data into 4 pieces based on, of course, indices, right? Assuming you have a big vector, you can easily find the corresponding index, starting index, and ending index for each chopped device chunk, for each chunk of data. And then each GPU can handle each chunk of data. You can do the parallel processing based on the way how you chop up the data, right? So you can use multiple threads to run on device, or you can use one thread to handle one device. If you are doing MPI programming, it's very, very common to have each MPI process to handle individual GPU. So you can do some mounting, like a mapping between the MPI rank to the local device ID. The concept here to the map is very similar to map the global index of your element array to your thread index. The device index, it's kind of like your thread index, right? When we are doing this CUDA programming. And then MPI index. Rank ID is kind of like your global index. So you need to do another layer of mapping if you do this multiple device kind of thing. And in many, many cases, you don't have homogeneous system. Some nodes has probably 4 devices. Some nodes have 8 devices. So when you're doing this partitioning of the chunks across multiple nodes, then you need to be more careful. You need to collect the distribution of the devices and have some information on your, rack 0 process, and then you start dividing your data by knowing which node has how many GPU devices and things like that. This is another level or layer of controlling, but conceptually it's straightforward because all the device index and the device count, they are just integers. Like the device, get a device here, you get a device for the particular device you are using, simply give you 0, 1, 2, 3, all the way up to the number of device minus 1. If you have 4 devices, your index is simply 0, 1, 2, 3, and you can use this and do this quick calculation to map with the MPI, rank ID. Another pretty commonly used function is called the device properties. This one, it will be helpful for you to extract the information about a particular device that you're working on. In many, many cases, you need to keep updating your CUDA code because for every generation of CUDA and a GPU, and the performance might not be easily portable. You might need to modify your code to make it work. But if you have some piece of code that can grab the device information and automate the process inside to fine-tune the configuration somehow based on the device configuration you may have here, like how many threads per block, how many multi-processors I have for this GPU, and how much memory I have, and etc. All this information could be grabbed from this function for the CUDA get device properties, which is very useful for you to write some more generic CUDA code kind of portable across multiple GPU devices or GPU clusters. Okay, I think that's all for device management, and also I mentioned about using MPI plus CUDA to write massively paralleled heterogeneous computing code. That's probably the ultimate goal because that's basically what the most state-of-the-art large-scale programmers are doing. They are developing some of the MPI plus CUDA plus something else. Could be OpenGL, could be some other libraries. But essentially, CUDA will give you the performance you may have, give you the maximum ceiling that you may have on a GPU. If you're using OpenCL and libraries, or even OpenC, you might not be able to reach to the maximum performance. Even OpenCL, I mentioned OpenCL mainly because it's supported by Intel, NVIDIA, all those big companies, but compared to some performance of some non-trivial applications, CUDA is always winning, almost always winning. Another big reason is that many of the real-world applications, they use the CUDA libraries, which is highly optimized. The libraries are highly optimized by NVIDIA engineers, and for OpenCL, it's kind of hard to compete with those libraries. So there are a lot of resources on CUDA website. You can find instructions, tutorials on YouTube, and there are a lot of instructions about how to do the debugging and the performance tuning. If you really want to get into the next step, I think the very next thing you want to learn is about how to use shared memory. You need to declare shared memory in your CUDA code, kernel code, or device code. And then you need to manually copy data from global memory to shared memory, and then try to utilize the shared memory as much as you can, and make sure you synchronize your threads whenever you need to move to the next step. But again, all the details goes into the mapping. The mapping will not be simply from the element index to the thread index and the block index. Now, if I'm using shared memory, the mapping will be mapping to the local shared memory size that you're dealing with. That'll give you another layer of complexity. which is actually non-trivial. Actually, you needed to be very careful about how you write your code and how you do the data synchronization. On one end, you want to minimize data synchronization. On the other end, you have to do it. Otherwise, your code will definitely not work as you expect. So I would like to acknowledge the NVIDIA Deep Learning Institute. They are providing this all the tutorials about CUDA and some other materials that NVIDIA Deep Learning has been supporting. They're also helping us to sponsor a lot of tutorials, and that we have been working closely with HPLC and TAMITS to host those workshops at HPLC and at TAMU. And we also want to thank HPLC and TAMITS for supporting, and of course, the support for Faster and ACES are tremendous to get everything working. And thanks a lot for ISF for supporting us and supporting the whole research community.